Hi everybody, I'm here to show you how to use LaGrange Interpolation. The idea behind it is very simple for a pretty complicated sounding name. And that is that a table can be broken up into a sum of multiple tables. So for instance, I could break this table into -2, 9, 1, 0, 3, 0. So notice that that first point is still the same. I could then add another table to that where -2, 0, 1, -6, and 3, 0 are the values. So can you already see, that the x values are staying the same, and that the y values, when you add them together, are starting to create the f of x table. And then we'll complete this with, again, the same x values. And now I will leave the point 3, 4 intact. Now, you might think, why are we doing this? Well, it's very useful to have a table with zeros in it. All right? If you looked at the original table, we don't know any of the zeros. But in each of the 3 tables you see in red, I have multiple zeros. And multiple zeros allow me to write the function in factored form. So basically, I'm going to be writing a function for each of these tables, and when those functions are added together, they will get us f of x. Okay, so here we go. So let's take a look at our first table. We know these 2 zeros, which means that we can write this as a quadratic, and we'll use this third point that's not a 0 to determine its a value. So let me set this up. So y equals a. Let's put our first factor in here from the 1, 0. That would come from the factor x minus 1. And then the 3 would give us the factor x minus 3. And now I'm going to substitute 9 in for y and -2 in for x. Notice that a is my only variable now, so I can solve for that. So I'm just going to keep simplifying here, and I find that a is 9/15, which actually simplifies to 3/5. So we have a quadratic function, y equals 3/5. Here we also have times x minus 1 zeros, x minus 3. We have another point that models going to help us find an a value for this quadratic. Let's go on to the next quadratic, y equals a, same way I was doing before. This has a factor of x plus 2 from that -2, 0, and x minus 3. I'm now going to substitute -6 in for y, 1 in for x. Again, a is my only variable. I can now solve for that. So a turns out to be 1 in this case. Great. So now the quadratic for this table is just 1, which I don't have to write, x plus 2 times x minus 3. Now on to our last table. Again, we have 2 zeros and a point to let us find our a value. So I'll be setting these up as a nice quadratic. Oops, that's plus 2. Substitute 4 in for y and 3 in for x. And what is this simplifying to? 4/10, which is really 2/5. So I have y equals 2/5 times x minus 1 times x plus 2. Now I have the function for each of these separate tables. So let's go back to the original question. So now let's fill in these functions. On the first table, we found out that that a value was 3/5. Our function, or their zeros, I say, were 1 and 3. The second table was a value of 1, x plus 2, x minus 3. And the last one was 2/5. This was x minus 1, x plus 2. So now notice, we have f of x. It's not in a form that we're used to seeing. It looks like we have a factored form, plus another factored form, plus another factored form, which doesn't make it factored form anymore. If you wanted to test this out, we could substitute in -2 and see if we get 9. Let me just demonstrate what happens when we do this up to one of the points. So if I do f of -2, and I substitute it in the first part, and I substitute in the second part, and I substitute in the third part, look what happens to the second and third parts. Look right there, it just happened. Right here. That -2 plus 2 is 0, so this entire value will be 0. It's going to happen here as well. That will cancel, and you'll just be left with this. And notice what table that came from. The table that had the -2, 9. If I substituted 1 in, I would get -6, because the first and third functions would cancel. Okay? So now, I just wanted to point out one other thing, and that is that we could turn this, whatever form we want to call it, into standard form. We could. We should get a quadratic, right? We're adding a quadratic, and a quadratic. You don't have to do that. In fact, I don't know if there's a great reason to do it, but I just want to show you that in the end, we'll get the quadratic that I was talking about. So here we would get 3/5 times x squared minus 4x plus 3. Here we would just get the x squared minus x minus 6. And here we'd get 2/5 times x squared plus 1 minus 2. Okay, so now let me just distribute the 3/5 and the 2/5. Notice 3/5 times -4, I just wrote that as -12/5. What is this? This is 9/5. Now I'm going to distribute the 2/5. And now I just need to combine my like terms. So here are my quadratics. So 3/5 and 2/5, oh that's nice, that adds up to 1. So 1x squared and 1x squared, that's x, oops, sorry, that's 2x squared. Let's go with the linears now. We have -12/5 x, positive 2/5 x. Okay, so that's -10/5 x, or -2x. And -1x, that makes -3x. Okay. And then the last part, our constants. We have 9/5 and -4/5. So together that makes 5/5 or 1. And -6 makes that -5. So we have this form of f of x, which there was nothing wrong with, but we also have standard form. Now standard form does look a lot nicer, it's easier to write, you can see it has integer coefficients, right? But it doesn't really matter all we really cared about was finding a function that models that table. So hopefully you can use this method when you aren't sure what type of polynomial would model a function.